Alright, so as far as quadric surfaces are concerned, you really do have to look at the list and make sure you know all of them. But I think it's important to also be able to construct them on your own and not have to rely on the list. So let's go ahead and do a couple examples. Over here we got x squared plus 3y squared minus 4z squared equals 0. First thing I'm going to notice before I do anything is the fact that this guy's got to go through the origin. Why? Because 0, 0, 0 is an answer to that equation. Okay? So that's a good mental note to keep in your head, just so you can sort of use it later. So now what I'm going to do is move the 4z squared to the other side because I don't like minuses. Okay? So x squared plus 3y squared is equal to 4z squared. And now what I've effectively done is separated the projection onto the xy plane. And remember, all that means is I'm looking at the surface from above, so that changes in z don't really faze me. I can't see them. If I'm looking at it directly from above, sort of when it's coming towards me, changes in the z direction, I can't tell. Okay? So the projection onto the xy plane is going to be a bunch of ellipses, right? Because of the x squared plus 3y squared. If you want, you can just block this and say that's just some constant. It's x squared plus 3y squared equals some constant. It's obviously going to be a bunch of ellipses. But what's important as well is the fact that the ellipses, how big they are, is also determined by the z component of this thing. Okay? So if you think of the ellipse as sort of having a radius, even though it doesn't really, but you can think of it as having a radius. That radius is determined by 4z squared. Okay? So what we can tell here is two things. Number one is that if I look at this thing from the above, so x, y, z, if I'm looking at it from above, it's got circular or elliptical projections onto the xy plane, but I also know that these things are growing as z is growing. So as I go further up, my projections are going to get bigger. My ellipses are going to get bigger. What I also know is that they're going to grow at the same rate because they're all squared. Okay? So as z goes up 1 unit, my ellipses are going to get bigger by 1 unit. Okay? So then that gives me all the information I need to know. So I'm drawing a bunch of ellipses, and they're getting bigger linearly as we're going up the z-axis. So I'm just drawing basically a cone. Okay? So that is, in fact, the formula for a cone. But that's why it constructs a cone. Okay? So let's go ahead and do this one. This is the same thing, except now, when I write it in this way, I can immediately see that it's very similar to that, except for the fact that the z is not squared anymore. Let's see what sort of a difference that makes. So I'm still going to have elliptical projections onto the xy plane, but now the rate at which they're growing is not linear anymore. It's not, if I said, okay, I'm going to forget about x over here for now. It's z squared equals y squared with some constants. I don't care about the constants. But z squared equals y squared, or z equals y. That's why the projection of this thing onto the zy plane is just a line, right? Well, it's not just a line, but you can think of the boundary as a line, okay? But over here, if I forget about x squared, it's going to be z equals y squared, okay? So I'm going to draw that like this. If this is z, this is y, z equals y squared is just this. Easy enough. It's just a parabola, right? Same thing with x squared. Z equals x squared. Something like that, right? And my cross-sections or projections on the xy plane are still circles or ellipses. So I'm going to have an ellipsoid, right? Instead of going sharp out, linearly out like a cone, it's going parabolically out. Okay? So there you have it. That's the second one. So the third one is a little more convoluted. It's z equals 2 times square root of x squared plus y squared. We don't like square roots, so we're going to square both sides. So now I can immediately see that I have a case of the same thing. It was just sort of hidden. I have x squared plus y squared equals z squared. Again, it's just going to be a cone. And again, it's going to be a cone because I got my elliptical projections, and they're growing linearly. So, bam. So now let's do this one. It's phi equals pi over 3. Okay. Technically isn't a quadric, although if we take it back to, yeah, this is actually not a quadric surface, but I just put it in there because it sometimes shows up on sort of tests and quizzes. So phi equals pi over 3 is just going to be, our phi is, remember, the angle that our vector makes with the z-axis. So this guy is just going to be pi over 3. Done. It's just a line. Over here, we got z equals x squared minus 3y squared. So it's very similar to this one, but with the exception that it's a minus now. So how would we do it? Okay. We're still going to take advantage of the same thing, the fact that our projections on the xy plane are going to be something that we know. This time they're not ellipses, they're hyperbolas. But still, they're the same sort of idea. And they're growing, not linearly, but just like this one, sort of like a parabola on the outside. Okay. Now these guys are sort of hard to draw, so I'm not going to probably do a good job, but you can sort of look up the actual image. But the important thing is that we can classify. And just like this one was a paraboloid, an elliptical paraboloid, because the projections were ellipses, this one is a hyperbolic paraboloid, because the projections on the xy plane are hyperbolas. Okay? So there you have it. That's a couple examples. I've left out hyperboloids of 1 sheet and 2 sheet just because they're a little harder, because hyperboloids are way harder to, just hyperbolas in general, especially when you get in 3 dimensions, they're harder to draw on a chalkboard. So it would become too messy. But we can take the same ideas and apply them to drawing hyperboloids. So there you got it, a couple quadric surfaces and this random shape. So there you have it.